Okay, I see that somebody has already started recording it, which is great. All right, so let me just share my desktop. And it has all this stuff, so I need this, and I need the slideshow. You able to see my slides? Yeah?
Yes, sir.
Okay, so this is just an enumeration of Bravais lattices. And this time around, we'll look at the Bravais lattices that arise in 3D. And so in 2D, in the previous lectures and sessions, we discussed crystal classes and lattices. And we saw that there are 4 crystal classes, basically a parallelogram, a rectangle, square, and a hexagon. And these 4 classes also give rise to 5 lattices. There are 5 different lattices which can be classified into these 4 crystal classes. That number is a little larger than the crystal classes because the rectangular symmetry allows for 2 different types of lattices with that symmetry. One is the centered rectangle, the other one is just a plain rectangle. So similarly, in 3D, we will see that there are 7 crystal classes. We will enumerate all of them. It's all fairly straightforward. And we will look at the symmetries that they possess. And then there are 14 Bravais lattices, which can be classified into these 7 crystal classes. Okay, a bit about geometry. In 2D, whether it is 2D or 3D, a lattice is essentially, this is a definition that I took from Wikipedia, an infinite array of discrete points generated by a set of discrete translation operations. What it means is that if you start with a point and you translate that point and generate all these other points using this vector r, which is defined in this fashion, n1a1 plus n2a2, where n1 and n2 are integers and a1 and a2 are non-collinear vectors. So as we have seen, a1 and a2, they form a parallelogram or a 2D unit cell. And we have been referring to that unit cell as a 2D brick, whose repetition gives rise to, or rather generates the entire lattice. Okay, same thing applies to 3D as well. So now we have a set of discrete translation operations in 3D. And again, the n's are the integers and the a's are non-coplanar vectors. And in this particular case, in 3D, A1, A2, A3 form a parallelepiped or a 3D unit cell or a 3D brick. Okay, going back to 2D, we also realized that A1 and A2, the magnitude of A1 and magnitude of A2 and the angle between the vectors, they together define a parallelogram. And the convention is to refer to them as A, B. A and B are the magnitudes of vectors A1 and A2 respectively. And theta is the angle between the vectors. And the crystal classification is essentially based on the values taken by these 3 parameters. So similarly in 3D, we have 3 vectors, and since they are non-coplanar, you also have the possibility of 3 angles between any 2 of these vectors. And so again, convention is to refer to the magnitudes of these vectors as A, B, and C, and then the angles as alpha, beta, and gamma. Just note this, alpha is the angle between B and C. That is, in other words, alpha is the angle associated with A, not containing A. So, and similarly, beta is the angle between the axes A and C. And similarly, gamma is the angle between axes A and B. So crystal classification again is based on the values of these three parameters. And now we are ready to start. The 7 crystal classes are basically these, which are listed here. We'll go through them one by one. Triclinic is the most generic, non-special in every aspect of these lattices. The unit cell is given here, and these are pictures that I took from Wikipedia. So A, B, and C are all distinct, and alpha, beta, gamma are all distinct and non-special. That is, special would be any of those angles such as 60 degrees, 90 degrees, 120 degrees, and 180 degrees, and so on. So we don't have any of those special values. And the only symmetry that this thing possesses is the trivial one, which is basically one-fold rotation about any axis. And that is basically 360-degree rotation about anything at all, any direction that you may choose as the rotation axis. And because they are all points, it also possesses the so-called inversion symmetry, where this symmetry is basically taking the point x, y, z and inverting it through the origin to take you to minus x, minus y, and minus z. And this is the equivalent of the generic parallelogram that we had seen in 2D. All right, some additional symmetry elements arise when you go to the monoclinic. And so they do have distinct values of A, B, and C. And alpha and gamma are 90 degrees, and beta is some non-special angle. And it is sort of interesting that they have chosen B as a special axis. And about this axis, it has twofold rotation symmetry. Because these angles are 90, twofold rotation symmetry will basically take this rectangle formed by A and C onto itself when you rotate it by 180 degrees about the B axis. And because of that, you also get this bonus symmetry, which is the mirror plane normal to the B axis, which is basically this plane here, formed by A and C. So you get this additional symmetry. One level higher is orthorhombic. Now A, B, and C are still distinct, but all three angles are 90 degrees. And because of this 90 degree, which is a special angle, you get more symmetries now. So you get a twofold rotation about the three axes here, A, B, and C. And because of that, you also get mirrors normal to all these twofold rotation axes. And going forward, one level higher, now we have a tetragonal system class, and in that A and B are identical, so they are referred to as A and A here, and C is distinct from those two. And now the three angles are 90, and because of the fact that A and B are the same, you get a fourfold. Okay, this must be fourfold rotation about the C axis, which is fairly obvious, and twofold rotation about A and B as well, which again is something that is inherited from the orthorhombic. And finally, you also get some bonus symmetries. These are twofold axes about the two diagonals. That is this diagonal going from here to there, and that diagonal going from there to there. And you also get mirrors normal to the fourfold and all the twofold axes. So you get all these symmetries. And we can actually count the number of symmetry elements, but all that you will encounter as you go to higher levels in your respective fields, whether it is physics or chemistry or math or materials. I mean, crystallography you may encounter in biology and earth sciences as well. All right, so now we have this cubic system. So we have fourfold about A, B, and C. And all of them are identical, and which is why they are referred to as using the same symbol A everywhere. And I don't know whether you see this or not, but this generates a threefold rotation about the body diagonals, starting from that corner to that corner. So if you take that body diagonal and rotate this anti-clockwise by 120 degrees, you generate the same lattice as well. And finally, 2 folds about the phase diagonals as well. And because of these facts, we get the mirrors normal to 4-fold and 2-fold axes as well. All right, so now we come to a slightly different class, rhombohedral, where A, B, and C, they're all identical. So they are given using this symbol A. And alpha, beta, and gamma are all identical, but they are not 90 degrees. In fact, they are not any of the other special angles. Those special angles have to be obtained a little bit more carefully, but it is some it's a generic non-special angle. You can imagine this as essentially a cubic unit cell, which is elongated or squished along a body diagonal. So if you take this cubic unit cell and you take this body diagonal going from this corner to that corner, one body diagonal, not all of them, obviously. You take one body diagonal and sort of pull this entire thing outwards or push them inwards. And what you end up getting is the rhombohedral crystal, which is why it has a 3-fold about that diagonal, that special axis. And so you end up classifying this as a separate crystal class. And finally, the hexagonal, we have already seen this. So here's the generating unit cell, which is a parallelepiped, and the angle here is 120 degrees. And the rest of it, you can also see how the entire hexagon can be generated using this unit cell. And of course, you keep repeating this in space, you get this 6-fold rotation about the C-axis, which is special, and A and B are the same, and C is different, and therefore you also end up getting 2-fold rotation about the A and B axis, as well as 2-fold about the phase diagonals. Phase diagonals being going from here to there, and there are 6 of them. So in the hexagon, but within this unit cell, this is the phase diagonal, and therefore you also get mirrors normal to all these axes. Okay, quickly. Now, how do you get Bravais lattices? Remember, we talked about centered lattices in 2D, and here, because we are talking about stuff in 3D, we get centers at the base. That is, there are 2 parallel planes which have a lattice point at their centers within the unit cell. And of course, body centered is something that you're familiar with. Face centered is something that you're familiar with. All these other unfilled boxes, you should be able to say, think through and prove that any of these other things would be equivalent to any of these other Bravais lattices. And I think I mentioned it in one of the previous classes. Somebody came up with 15 lattices, and Bravais' contribution, one of the contributions, of course, he proved the existence of these 14 distinct lattices rather rigorously. But along the way, he also showed that 2 of the 15 that was generated by this other guy, I keep forgetting his name, but I think I've already mentioned his name in the chat box earlier. They are basically the same. So we'll see how these things work out. In triclinic, there is only one, and it is the primitive cell. And in monoclinic, you have the primitive version as well as the base-centered version. So you have this stuff here. And so orthorhombic, you have, I mean, all possibilities. Here is a base-center. These, the bottom plane and the top plane, they have a lattice point at the center. This is equivalent to, suppose you get rid of the third axis. If you look at the bottom plane here, then that is a rectangle. And in the rectangular case, we saw that the centered rectangle was also one of the 2D lattices. And this is basically something that is generated from this centered rectangle into the third dimension. But of course, these two do not have any analogs in 2D. So here is a body-centered version, and here is a face-centered version. In tetragonal, we have only these two. And you might want to check out why, for example, the base-centered tetragonal version does not exist. In other words, it must be equivalent to one of the others. And similarly, face-centered tetragonal is also equivalent to one of the other examples that we have looked at. Right, so here is cubic. So famously, it does not have the base-centered version. You can sort of see if you put a lattice site here and here, for example, you completely destroy the cubic symmetry. What do we mean by cubic symmetry? There are two key things here. One is the threefold axis about the body diagonal, each of the four body diagonals, and you break that symmetry. So it becomes tetragonal, obviously. And of course, the other symmetry element that is broken is that along the z-axis, along the c-axis, you still have the fourfold symmetry, but along the b-axis here and the a-axis along this direction, you destroy the fourfold symmetry, obviously, and therefore that does not exist. In a similar fashion, you should be able to convince yourself that any of these other possibilities would not work. Rhombohedral, there is only one version, and hexagonal, there is only one version. And so here are these things in red, which correspond to all these other kinds of lattices that one could generate, but they don't work. In other words, if you do generate lattices of this kind, then they would be equivalent to one of the 14 Bravais lattices. Just try this as an exercise, at least for a couple of them. In the class of monoclinic to cubic, so there are only 1, 2, 3, 4, and 5. Just check them out and convince yourself that they do work out all right. Okay, with that, we are basically done. So let me go back to the class. All right, so that took a while, but we are done. So any questions? Hello.
So can you please explain about base-centered lattices? Base-centered cubic lattice.
Base-centered cubic. Just there are 6 faces, right?
Yes, sir.
Three sets of parallel planes.
Yes, sir.
Each having two parallel planes, right? Take one set and put something at the center.
Yes, sir.
Okay. So that is what one means by base-centered. It is also sometimes referred to as end-centered lattice. So you remember the centered rectangle, right?
Yes, sir.
In 2D.
Yes, sir.
Yeah. So just generate a 3D version of it. Then you have one centered rectangle at the bottom, another centered rectangle at the top, and connect them through these other 4 lines, and then you generate the parallelepiped, right?
So is it like parallel planes have an atom at the center of the face?
Not atom. We are talking about lattices now. So yeah,
Yes.
a lattice point at the center of one set of parallel planes out of these 3.
Yes, sir. Thank you.
If it is face-centered, all the 3 sets have something at the center, right? That is called face-centered lattice. You have face-centered cubic and face-centered orthorhombic and so on. And this is taking only one center and I mean one set of parallel planes either the ones made up of A and B, or B and C, or C and A. Just take one of them and put a lattice point at the center.
Yes, sir. Thank you.
Yeah, it is. I mean, if you really think about it, it is interesting. In the case of 2D lattices, we said a centered parallelogram doesn't work because a generic parallelogram with a lattice point at the center doesn't work because you can generate another parallelogram using that center and the one at the corner, and well, that would possess the same symmetry as the original, I mean, parallelogram itself, and therefore it is equivalent to a primitive parallelogram. So whereas in monoclinic, you have something which is centered. Anyway, so that's an aside. Any other questions? Yeah.
So in any lattice, we just compare the symmetry of that lattice. Is it due to that the lattice get replicated in the main structure, or is it because every different lattice has different symmetries? Like, why is it necessary?
The 7 classes are based essentially on the symmetries, right? We looked at all those symmetries, and as you keep going up from triclinic, you get additional symmetries. So because of that, they are classified as into different buckets, right? And then, but you can generate lattices. For example, take the example of the cubic crystal class. So it has, the body-centered version has exactly the same set of operations as the primitive lattice, but obviously it has one extra lattice point at the center. Therefore, I mean, it is special. I mean, you cannot generate the body-centered version from the primitive. You cannot make them sort of equivalent, right? So that is why, I mean, we treat that as a distinct class.
So,
Yeah.
I had a doubt. So I was saying, why does tetragonal not have a base-centered symmetry? Because if orthorhombic has that, shouldn't tetragonal also have it?
Do it. I mean, just do a quick sketch and see that it is equivalent to a simple tetragonal. For example, go to the 2D version, take the square, for example. Right?
Okay.
If you have a centered version of a square, is it also equivalent to a smaller square, right?
Yes.
With the axes being half the diagonals? Just do it quickly.
It is.
You can see it yourself in 2D. It's clear. That's why, I mean, I started with 2D. Many things become very clear in 2D itself. So there is no centered square lattice in 2D because you can generate another square in which the basis vectors are half the diagonals.
Right. Okay.
Right. Exactly the same thing applies to tetragonal as well. So if you put something at the base, then it is equivalent to a simple tetragonal. Okay, by using a similar construction, you will be able to show that a face-centered tetragonal is also equivalent to body-centered tetragonal. So you have the option of picking one of the two.
Right.
But body-centered tetragonal is the one that.
So we just use body-centered instead. Okay, sir. Yes, sir.
Yeah, you got that. The face-centered tetragonal, face.
Yeah.
So all the 6 faces having a lattice point at the center, if you take that, you can generate a smaller tetragonal unit cell with a body center.
Yes, I got that. Thank you.
Yeah. So therefore, I mean, so you might use this as an interesting exercise. I mean, show that the others don't really work. Right? Trigonal, I mean, triclinic has no symmetry at all. So in principle, you can generate any other lattice and that would also possess just the triclinic symmetry. So there's no point in thinking about body-centered triclinic and so on and so forth. I will send you a separate note about how to generate the primitive versions of BCC and FCC. And when you draw those parallelepipeds, you realize that from the appearance, you cannot make out all the symmetry elements that it possesses. But yeah, which is why, I mean, we think in terms of body-centered cubic and face-centered cubic. By the way, I mean, all these lattices, you can generate the primitive versions, including the body-centered and face-centered version. I'll send you a picture later. I'll put it in the chat box as well. You take a look at that. But except that, if you look at that unit cell, you'll be left wondering where all the symmetries appear in the unit cell, which is why, I mean, one uses this version of Bravais lattices. So we think of them as cubic with a center, with a lattice point at the body center, or a cubic with a lattice site at each of the face centers. Yeah, any other questions?
Hello. Means
Yeah.
how we prove that any two lattice structures are equivalent means how we means write it down mathematic means rigorously means I was wondering.
I mean, I appeal to geometry. You can visualize it easily.
But sir, suppose I have to means
Right.
show it to someone
So,
rigorously.
Yeah. I'll send you maybe a couple of pages. I went and got the English translation of Bravais' book, and I'll send you a couple of pages. I'll scan it and send it across to you. You take a look at how, I mean, he used various geometric arguments to show that they do all the right things and they possess all these symmetries. But I'm not a mathematician, so I wouldn't want to go down that line. But I can only appeal to geometry visualization, which is very easy. I mean, these are all pretty simple things. Especially in 2D, they are trivial. You just do a simple drawing and you know that one is equivalent to the other. In terms of symmetry, I'm not saying that the unit cells are identical, right? The centered cubic, I mean, centered square, you can convert that into another primitive square, but the sides are not the same. But in terms of the relevant symmetry operations, what are the symmetry operations in cubic? You have mirrors about A and B, and you have mirrors about the diagonals. So the primitive, the new primitive that you construct based on the centered square, it has all those symmetries. So what is the need for the centered square? You see what I mean?
Yes, sir.
Yeah, I mean, I have no access to a board here, so I'm talking to you over a computer. But if it was a real class, I mean, it's 10 seconds to show it right away. You'll be able to see it. But I'm appealing to you to actually do it live. You can just draw something right away and you can prove it to yourself. But obviously, I mean, you've all done geometry proofs, right? Back in classes 9, 10, I don't know, maybe 11 and 12 as well. And so that is a kind of proofs that Bravais developed, and it's a book with about 120 pages or so. Let me see if I have it handy here. Ha, prized possession. There it is. And I even marked a page where he has a footnote. And he says, Frankenheim, I mean, he gives a reference to his work, and he says there are 3 distinct modes for the monoclinic, and Bravais basically shows that 2 of them are equivalent. So he lists those 3, and then he says it is easily seen that modes 2 and 3 are redundant. In other words, I mean, they are equivalent to one another. You just pick one of them. And the ones that he is talking about are the equivalents of the base-centered monoclinic. Okay, anyway, rigorous mathematical proofs using geometric arguments would be, I mean, somewhat similar to the ones that you used earlier. But right now in this intro lecture, intro class, I think it is enough for us to appeal to your geometric intuition rather than rigorous proofs. Anything else? No, nothing at all. Okay, so I'll send you this a couple of pictures. I will have to locate those pictures. I don't know where they are, but you can, for example, I'll send you a picture that will demonstrate that you can generate the FCC lattice using a primitive unit cell, and that would be a rhombohedral unit cell with a very special angle. And similarly, body-centered cubic can also be generated using that. So in principle, I mean, all these centered lattices, you can create the primitive versions, but the primitive versions are not used simply because the symmetry of the lattice is not apparent when you look at the underlying unit cell. And that is why one doesn't make use of those primitive unit cells for FCC and BCC and so on. And we actually think in terms of body-centered and face-centered unit cells, in which the number of lattice points per unit cell is more than 1. So, I mean, that's the way it is done. Okay, I'll send you that, and I'll send you maybe a couple of sample pages from Bravais' book, just so that some of you can see the kind of geometric arguments that would go into showing symmetry operations. For example, one of the arguments that he would use is to say that when you have a 2-fold rotation going along one direction and another 2-fold rotation going along another direction which is perpendicular to the original one, right? We are talking about something like orthorhombic now. The direction which is mutually perpendicular to both of them automatically develops a 2-fold axis. I mean, he shows that rigorously. But yeah, we just go ahead and say that in orthorhombic, you have this 2-fold axis along A, B, and C. But the point that he raises is that if you have a 2-fold axis along A and 2-fold axis along B, and A and B are sort of perpendicular to each other, then, I mean, you have to generate in a lattice a 2-fold axis along C, and C also has to be perpendicular to A and B. I think that's a pretty neat proof, and he does that. And so it's kind of nice. Anything else? Okay, we are at 10 past 10.
Yes, sir.
Yeah, there is one question. Yeah.
I was drawing the edge-centered monoclinic system that is out. And how come we can't take the again half the diagonals of the parallelogram faces to get a primitive cell?
Okay. There was some disturbance in the question in the way your voice came through. Can you just repeat that?
Yes, sir. Am I audible now?
Yeah.
Okay. So when you draw the monoclinic end centered lattice, like
So you're talking about the end-centered monoclinic or base-centered monoclinic. Yeah,
yes,
what's the question?
right. So why can't we take again like half the diagonals as the sides and generate a primitive lattice from it?
Okay, try it.
I drew it. I
Okay.
think it works.
If you're unable to see it, then maybe I will just post a quick note.
Okay.
So I'll try it myself, take a picture and then post it. So,
All right. Thank you, sir.
okay. First of all, you will realize that it will break the symmetry.
Okay.
Okay, the symmetry that we are talking about is the two-fold axis about B.
About B, right?
That will
Okay.
go. Okay. If you do this, I mean, take the picture that I sent you. I will also post the presentation in the files folder there. You take a look at that stuff, or you take a look at what is there in Wikipedia. Just reproduce it on in your notebook and see for yourself that monoclinic has just one symmetry, and of course there is an associated symmetry, which is the mirror plane perpendicular to the two-fold axis, right? But just focus on the two-fold. If you do it using that method, you will destroy the two-fold. Okay. So I will leave it there. If you are unable to see it, put a comment in the chat box, and I will do it in my own way and send it across to you. But it's a little confusing. Please be careful. B is a special axis here.
Okay.
Okay, but and therefore the faces which have a lattice point at the center are things containing the B axis. It is, I think, in the picture. Let me just look at the stuff myself, and I'll come back to it. Yeah, so the base that we are talking about is the one that the face that contains A and B. And remember, B is a special axis here. And therefore, if you do it, if you just go through that construction, and you will realize that at least at the unit cell level, you don't see. You can always, by the way, you can, like I said, you can always convert any centered lattice into a set of primitive lattices. But if you look at those unit cells, they would all look odd. The symmetry of the underlying lattice will not be apparent in the unit cell that you're looking at. Okay, so that's why, we think in terms of body-centered cubic as a separate lattice. But you can generate a nice primitive lattice, primitive as in just one lattice point per unit cell. But you look at that brick, that parallelepiped, and you will be left scratching your head as to, where are all these, threefold axes? There are 4 of them when you look at a cube, 4 different body diagonals. Each of them has a threefold axis, and you won't see it in that shape. You just will not. So that is why, we decide to dump this primitive lattice notion, and we use a unit cell such as BCC and FCC, which reflects the complete symmetry of the lattice. Yeah. Well, try it, and if you still don't see it, let me know. I'll post a picture.
All right, sir.
All right. Anything else? Okay, so let's end the meeting here now, and we'll meet again Monday. and I'll post a bunch of things in the chat area, and I'll also send you the home assignment, basically from the crystallography chapter of Callister today, so by this evening. Okay, we are done now, so I'll see you on Monday.